analytic function plus another one whose leading term is z38 times something. Okay? So this means that when I do one of these limits as intermediate channel is going to run an infinite number of states coming from the identity and an infinite number of states coming from the energy. How I can distinguish the two? Because they have different power law. So the way of fixing the overall constant is making this limit, seeing what is the term of my function which will behave like this and normalize to 1. Okay? So if you do that, the story is very simple. So if you do x 2, 3 going to 0, for instance, you can check that x is going to 1. And you will see that this term is going to a constant, which is 2. And then you have immediately under your eyes the singularity of the identity family. Because when you put z and z bar, this will become modulus 1, 4. So this term here, which is under your eyes, with this normalization has to be 1. So the condition is twice times a has to be 1. Therefore, a is equal 1/2. Finished. This is my correlation function. And now if I look the other singularity, please do the exercise. The coefficient that I found, because at this point is fixed everything. I have no longer choice. What you find, exercise for you, is that in this simple way, the structure constant is 1/2. I will, yeah. So what I'm saying is, once I pin down to the best of my information, the 4-point function, typically remain an overall number in front. This has to be, because everything is linear. So it has to be like this. The point is how you can fix this overall constant. And the recipe is look for the channel of identities. Because the channel of identity, for the way we normalize the field, is normalized to 1. So if I go to my correlation function, taking the limit, and identify what is the term which behave as the identity channel should work it out, since these are imposed to be 1, the coefficient is fixed. So apply this criteria in these cases. The thing is like this. If I do the limit, which I was doing before, z 2, 3 goes to 0, so I'm checking the intermediate one. So I'm checking sigma, 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 sigma. I'm contracting this with this. So I'm doing this channel. If I do this, you see that there is explicitly 1 minus x modulus minus 1, 4. So this is the channel I'm looking for, under my eyes. How much is this? You compute the limit, and turns out to be a number, 2. Since you want this guy to be normalized to 1 in this channel, therefore a times 2 has to be 1. A equal 1/2. At this point, fixed, finished. But once I have this, I can go to the other channel. So I have to look what is the other channel which behave like modulus 3, 4. I leave to you the exercise. And once you identify the term which is modulus 3, 4, the number which is in front is the structure constant square. Because remember, epsilon epsilon give rise here, so there is one structure constant, sigma, sigma, epsilon, but the same structure constant will be here. So you will have c squared, or what you are looking for, equal to the value of the function you're looking. So in this case, it will become 1, 4. You have still the ambiguity of the sign, because it's always quadratic relation. But this, you can check explicitly that the fusion rule is an automorphism. Namely, if you have a field, you can redefine a new field with the minus sign. The algebra remains the same. So this sign is irrelevant. So at this point, once you have a quadratic relation, it's up to you how you choose the sign. But this means in diagonal channel, because if you go in a different channel, you might have non-trivial interference. So if you have structure constant of one channel times structure constant of another one, the sign matter at that point. It's no longer the square, but is what it is. Okay, so I strongly advise you to do this exercise once. It's in the paper of Belavin Polygon Zoological in full detail, but I just want to do it to see in practice how the story, because there is a very smart way, although technical, to avoid the basic step I told you. So let me rephrase what the problem is and how you can jump to the conclusion. So the problem is, so we say we have to compute 4-point function of arbitrary primary field. I'm denoted by this. We can do it because with respect to any one, I can work it out the linear differential equation. But I say the story is painful because you have to find out the precise null vector condition. So this is simple for level 2, level 3, level 4 start to be hard. Myself, I never went up to level 5. And believe me, it's painful. So in principle is there. In principle is algorithmic, this story. So you can program a computer to do for you. But honestly, it's something complicated. Now, what is the approach, the real magic approach of Dosenko and Fatev, which are the other bunch of paper I gave you, is that they have a magic box, literally, to not computing the null vector, not computing the differential equation, but giving immediately to you the solution. Is amazing. Okay? So they don't do the first step, they don't do the second, and they say, look, this is the solution what you're looking for. Okay? How they are doing. So this is the black magic of Coulomb gas. So the physical idea behind is very, very interesting, because minimal models at the deep level, I told you, can be considered as a quantum group reduction of bosons. So it's like the father of all this theory is a bosonic theory in which you are cutting some degrees of freedom consistently. So the starting point of the Dosenko-Fatev method is to look the massless free bosons. So massless free bosons. Now, we discussed briefly another time that this is a very sick theory on which the boson itself you have to handle with care, but you can make composite fields which are perfectly defined objects. So the correlation function field in Z and Z bar, I'm going to take minus 2 log Z divided by A, minus 2 log Z bar divided by A, and minus 2 log of R over A at the origin. This, as you will see, immediately is a regularization of this theory, which is simultaneously ultraviolet and infrared. Okay? So So the theory is sick because Z, of course, doesn't make any sense alone. You have to divide by length scale. A priori, you could divide by ultraviolet scale, but I could have divided by R. So this is the problem. So this is a choice, okay? It's a choice of regularized propagator of massless bosons. So with these things, you introduce what is called vertex operator. Vertex operator is exponential I alpha phi of Z. Okay? So these are basic objects in the theory. For instance, in string theory, vertex operators are associated to the insertion of excitations. You can make puncture in Riemann surface, insert in the vertex operator. So, since the theory is free, I'm talking C equal 1. So this theory is C equal 1, and a scalar bosonic field. But I have to end up to my minimal models that, remember, was 1 minus something. So I have to subtract some degrees of freedom, okay? Now, remaining at the level of massless bosons, I can immediately compute by path integral or by big theorem, because the theory is free, what are the correlation function of arbitrary number of vertex operator. I'm just using Z, but the same will be for Z bar and so on. Now, this correlation function is product I different from J, Zi J divide A 2 alpha I 2 alpha J, and a prefactor which is A over R sum of alpha E squared. How I compute this one?
Maybe comparator formula.
Bravo. So when you have E alpha phi phi E I beta phi, you are doing this. What you have to do is to reduce this to a unique exponential contracting. But when you contract two fields, you have the logarithmic. Exponential logarithmic is power. Okay? So do it. It's very simple. So vertex operator is a power law behavior in which the channel I and J stay for Zi minus Zj, means you are contracting this, is Wick theorem, yeah.
Could you comment this one a bit better?
Is massless free bosons theory. So you can do by Wick. So if you have by this, you have to do possible contraction pairwise. So the only problem you have is how to compute 2-point function of these things. Now, this 2-point function of separate point, first you do Bagger-Hausdorff, you combine a single exponential, and then you make the average. The correlator of these things is logarithmic, and exponential logarithmic is power law. Do it. I mean, once you do, you will see it's trivial things.
But this type, also show Bagger-Hausdorff formula, it takes this expansion of the theorem or?
No, you can do directly with the exponential. If you don't like it, let's do another way.
I mean, what is the exponent?
Eh? What is?
The exponent is something not trivial.
These are the exponents, the charges.
The one with the average.
It turns out to be these guys. Yeah, I mean, work it out. I mean, you want to work for you. I mean, do it. I'm just telling you the idea. Another way of doing, if you don't like it, another way is, this guy is Gaussian theory, because the action is just de phi bar. So it's quadratic. So when you do any average, will become Gaussian integral. And Gaussian integral or logarithmic correlator are powers. Okay? Now notice what is the structure of these things. The structure of this thing is, first of all, there is an explicit A dependence which multiply the differences. So I can take it over, this one, if I define normal order operators, which is limit A goes to 0, A 2 alpha square, previous one. Okay? So saying in a human being language means when you do big contraction, please do not contract the field with itself. Means exactly like this. Now this will take care of this part. But you will see there is an infrared part which depends on the sum of these exponents, which in analogy with statistical mechanics is called charges. Indeed, this is a bunch of Coulomb gas, so you have in the plane charges, alpha, and you are asking the correlation function of them. Now, it's well-known fact that two-dimensional Coulomb gas is unstable unless the charge is 0, the total one. Here we can see here, because at the end of the day R is a regulator, to take R goes to infinity such that the theory is no longer sensible to the infrared cutoff. So the only way I can realize this is that if the total charge of correlation is going to be 0. So there is a very simple rule of thumb. The rule of thumb for vertex operator in free theory is alpha 1, alpha 2 is exponential 2i alpha 1, alpha 2. Here is the logarithmic, and there is the minus 1. So here will become z1j, 2 alpha I, alpha j. So this is the individual correlation. Okay? But if you have a bunch of them, the total sum, alias the sum of these charges, has to be 0. So you see immediately the only 2-point function which is non-zero is when you have the vertex operator and the other with minus 1. And this is 1 over z2 alpha square. Okay? Out of which the dimension, the vertex operator, is alpha square. Because remember, the channel of identity, delta. So, this is the point. What is the stress energy tensor of this theory? Very simple. The stress energy tensor we computed the other time is a nadir. The stress energy tensor is T is equal minus one-fourth the phi square. So this is the z bar part. So if you computed Tz1, Tz2, you get 1 over 4, z1 minus z2, 4, therefore c equal 1. So what is the message of all this? The message is you can have a beautiful, consistent, conformal field theory made of massless boson fields. The central charge is 1. The primary field are the vertex operator. I can compute all the correlation function I like, and then finish. It's a nice theory, but no more than that. Okay? This is an example, explicit example of conformal field theory with C equal 1. This, of course, does not solve our problem because we want to address something which is quantized in terms of two integers and anomalous dimension which are quantized as well. You see, here alpha is any values.
So alpha here in plane role of RNS.
Yeah, no, I'm saying, so let me tell you what is the guiding rod. The guiding rod is, I have conformal field theory is equal 1, which is fully consistent theory. What I'm going to do is try to reduce the degrees of freedom of my bosonic field such that the central charge is not 1, but is something less than 1. And moreover, I'm going to represent my primary field of the minimal models in terms of proper vertex operator with quantized charges of this one. So this is the guiding rod. So say differently, the bosonic field is so flexible that can emulate, can simulate, can act as. This is the point. So the bosonic field is so power that as far as I restrict properly its degrees of freedom, it behaves as the minimal model. This is the idea. Okay? So how I can modify my system to do like that? Now, we have to refer to a basic property of correlation function in field theory, which are dictated by, axiom like Whiteman axiom and this and that. What I mean is, if I give you a function of some variable, and I ask you, this function can be correlation function of some field theory, the answer is, in general, not. Okay? A function, different variable, to be correlation function of some local field theory should satisfy a set of axioms. For instance, translation invariance means they should depend on differences, cannot depend on the individual values. Should have cluster, should have this and that. So there are a set of things. So what I want to do is unbalance this neutrality condition, putting into the game a vertex operator with some charges that I'm going to hide. So the idea is the Coulomb gas has to be overall neutral. So the sum of all these charges has to be neutral. But imagine that at the second desk I hide a strong charges 24, that you don't see it. Now, in order to be consistent, the sum of all the other people I see has to be minus 24. So it's no longer to be 0, but overall has to be 0, with a term that you don't see it. So the idea is I have to insert a vertex operator which takes care of this unbalance of the charges. The point is, if I have my plane with a sphere, where the hell I can put these extra charges? Such that what is left out is an honest correlation function of something. And there is a unique answer. The only point you can put this extra vertex is at infinity. There is no other point. Because if I put a finite one, since everything will depend on differences, you will find some strange function which depends z2 minus 4, z6 minus 4. What is this for? You see what I mean? So the only place where you can hide an extra charges is at infinity. Therefore is what I'm going to do. So what I'm going to do is defining my new theory, which is called modified Coulomb gas, in the following way.
Sorry, could I ask you you hide the one affinity, but still the ones to balance them are still there.
Overall has to be 0, yeah.
Where are the rest though? Where are
Look, let me write, you will see. I will define the new average is in the following way. Limit r goes to infinity, r 8 times alpha 0 square So the thing is, this is a but this is n plus 1 point function. So I insert an extra vertex charges minus 12 at 0, and I send it to infinity. Okay? The amazing thing is that if you take the formula I just erased, you will check that what is defined by this limit satisfy all the axioms of correlation functions. So can be a correlation function. Okay? So I'm hiding here extra charges minus 12 at 0. You don't see any longer. But in order this correlation function to be different from 0, the sum of the charges now has to be 2 alpha 0. Okay? And now let's go to the 2-point function. What are the and non-zero 2-point function? The one whose charges is 2 alpha. And what it is, this is z, 2 alpha, alpha minus 2 alpha 0. Alias, the dimension now, this vertex operator, now you should start to ring a bell. Because you remember that my Katz table as a symmetry means I can represent the same fields in different points of the Katz table. When I modify these things, means I can represent the same identical field in terms of 2 charges. Okay?
So that symmetry comes from the neutrality of the charge.
Yeah. Okay? Now, I want now this guy to be a primary field. This is the hard part. Primary field means that I have to do operator product expansion with Tz with these fields. Remember, if this is primary, this has to be like this. So the residue of the pole should now become this function which is no longer balanced. Now, big theorem again tell you that if you use this stress energy tensor, you can never achieve this one. Never. So you have to modify the stress energy tensor in such a way that this guy is a primary. Can we do it? Yes, because the stress energy tensor is intrinsically ambiguous. I can modify this with a divergence which is second derivative. When you do Nader, remember that you have always an integral. And you disregard saying that this guy goes to 0 at infinity. But at infinity here, there is something. So you are changing the boundary condition. So this means that the new class of stress energy tensor has to be this one. Can be modified. Now, once you have this, let's compute now the 2-point function of t and t, because this will give us the central charge. Now, this is a beautiful exercise. So this was the previous term, so minus 1/4 second derivative this, plus A, these things, minus 1/4 delta things plus A second derivatives. Now, I'm going to sketch you the calculation because it's very simple. You have to do contraction of Wick. This term is Z2 even. So the only way it can have a non-zero term is this one. And this gives the previous C, which is 1. And this term can only contract with this one. Now remember that phi has logarithmic correlators. If you take 4 derivative, it comes out 1 over Z4, which is exactly the things. And what is the story? Minus A squared minus A squared. So this is the new charges, which is negative, different from 1. And fixing the anomalous dimension to be this, actually, sorry, it's plus 1, but A turns out to be I square root 24 alpha 0. So at the end of the day, the C is equal to 1 minus 24 alpha 0 square. So what I'm doing, I'm telling you how to fix this extra constant. What you have to do is stress energy tensor is the previous one plus this other guy. You impose this word identity, but you know what delta is. Delta is this. So how you have to fix the big A such that this guy is that one? And in this case, A turns out to be I alpha 0. And when you do the Wick contraction, because there are derivative, 4 derivative, you get the 24, which is here. So the main message of this calculation is if you modify the Coulomb gas, you are able to reduce the central charge, less than 1, and then you recover already the symmetry of the Katz table or the minimal model. So what is left out? To show that this quantity is quantized, and moreover, to be able to compute this correlation function. Okay? Now, I cannot show you the quantization of these things. This is a highly business concerned with BRST, symmetry, and all of that. So I'm not going to do it. But you can prove it that this one can be put in correspondence with the minimal model themselves. Okay? So this means that alpha 0 is quantized. Alpha 0 square is whatever is here. Now, we have the problem of delta Rs. So let me show you what the problem is and how beautiful the story is. Problem is that, remember that from what conformal field theory is concerned, you are only sensitive to delta. But given delta, in our Coulomb gas, I can represent this field either like this or like this. I have 2 equivalent ways. Okay? So given delta, I have 2 fields of different charges which are exactly the same. Now, consider the 4-point function of like this. The same field. This term has to be definitely different from 0. Why so? Because you see, in this channel definitely should be the identity, plus something else. In this channel should be the identity, and identity with identity fused to identity. So if I do all the operator progress function, this reduces to something which is positive. because it's all the square of something. So this guy exists, is positive and different from 0. Okay? Now, in this approach, I can represent one of these fields either with V alpha or with 2 alpha 0 minus alpha. Because I want to, if I believe that this field can be represented by this vertex operator, I can do it. So you have 16 choices. Because you can put here V alpha, V alpha, V alpha, V2 alpha 0 minus alpha and the rest. So for any of them, you have 2 choices. Now, do it. No matter how you do it, the sum of the corresponding charges, because will be charges anyway, never is going to be 2 alpha 0. And then you say, my God, I'm in a problem. Why in a problem? Because I told you this guy has to be different from 0. I say that this field can be represented in terms of vertex operator, and no matter how I do it, I never am able to satisfy the neutrality condition. Therefore, from vertex operator point of view, this function is 0. So you have a mismatch, something that is non-zero with something which is 0. How can we solve this paradox? And the way is very, very simple and nice. The way is to introduce operators which do not carry dimension, but carry charges, able to screen the extra charges. So what can be these operators? Can only be charges of dimension 0, obtained as contour integral dz of quantity which has dimension 1. Okay? So this means that once you give me some representative of the charges, I will have some extra charges that I have to screen, and then I can insert some of this Q to absorb these extra things. So let's compute these things. Since this guy has to be dimension 1 and can be represented by vertex operator, I have the equation 2 alpha 0 has to be 1. Therefore, there are 2 charges, alpha plus, which is alpha 0 plus square root 1 plus alpha 0 square, and alpha minus, which is alpha 0 minus 1 plus alpha 0 square. Okay? Therefore, here I have 2 possible operators, which I define this way. Okay? And so, let me give you an example how the story works. Imagine that this correlation function I'm giving you, I choose the representation to be V alpha with V alpha, 2 alpha 0 minus alpha. It's one of the possible 16. Okay? What is the total charges here? The total charge is 2 alpha 0, 2 alpha, because the extra charge, because I have alpha, 2 alpha, 3 alpha minus alpha is 2 alpha plus 2 alpha 0. This has to be equal to alpha 0. Now, the only solution seems to be alpha to be 0, but alpha equals 0 is the identity. So the only way I can make this guy different from 0 is that if this term is quantized in terms of these extra charges. Because at this point, to screen these extra things, I will introduce Q plus n times and Q minus m times. At this point, this correlator is different from 0, and I can compute it. How? You see, all these things are vertex operator. The one I computed before, the only thing is left out is these multi-integral equations, because Q is an integral. Now, we have no time to enter in detail. What I give you is the integral representation of the solutions of the theory. So if you work it out in detail, you will find there are hypergeometric, there are Kuhn functions, there are all kinds of solutions of the differential equation I was telling you before. So without computing any differential equation, I provide for you the integral expression for the correlation function. And once you have it, you do exactly the same business as before. You find a basis, which if you read the Dosenko-Fatev paper, correspond to the number of independent contours that you can choose it. It's a fantastic paper, ever read, because it's really the quintessence of analytic functions. So you have contour integral that you can deform up to the branch. How to do the analytic continuation? This defines the independent contour. Any independent contour is defining an independent integral representation of the function, and you repeat the same business as before. You go to the channel of identity, you normalize your function. You go to the other channel, you extract all the structure constant. So if you do this in full glory, you can find easily essentially all correlation functions of your theory. So let me give you some example. So for instance, you can take imagine you take this correlation function. You see that this correlation function has one channel of identity that I can use to normalize it. But once I do it, phi12 is expanding identity plus structure constant 1, 2, 1, 2, 1, 3, phi13. So the corresponding residue will be proportional to phi13, phi13, phi13. But remember, 3-point function is the structure constant. So this will be 1, 3, 1, 3, 1, 3. But here there are 1, 2, 1, 2, 1, 3. So, making the story short, you will have, just using the simplest integral representation, the way of computing these numbers. 1, 2, 1, 1, 1, 2, 1, 2, 1, 3, times 1, 3, 1, 3, 1, 3. And this is a bunch of gamma functions that I can write for you. I mean, I have to trace back all the anomalous dimension, things like that, but at the end is ratio of gamma function. Okay? If you look at the Dosenko-Fatev paper, is one of the end page, product, ratio, but it's all exact. Absolutely stunning exact. How do I know? Because once I was so curious, say, but cannot be the theory really sensitive to this bloody term. So what I did is I used to do numerics. Now you see that even if you insert a structure constant, which is 1%, because I put as a error 1% with respect to the previous one, the exact one, the spectrum turns out to be wrong. So it means the theory is extraordinarily sensitive to these values, by extraordinarily sensitive. So the number are really fine-tuning to the astronomical precision. Has to be that one, nothing else. Okay? So this is fantastic. I want just to give you a very, very quick reason for that. When you have easing in low temperature phases, you have two vacua that has to be degenerate. But easing in high temperature phase is something which is like this. Now imagine that I study with my technique of conformal field theory plus adding T minus Tc, the energy. So if I write down the matrix element with the things in the basis 1 epsilon sigma, the matrix is block form. So this means that you get some bunch of eigenvalues here, which has nothing to do with the bunch of eigenvalues there, a priori. But if you change the sign, the spectrum has to change with something which is a gap, like this, to something which has no gap, which is like this. And how you can realize this situation? If these highest eigenvalues, which come from here, smash with the other one. A priori, they don't know anything about one to the other. So at this point, if you spoil the structure constant only for 1%, you never see this phenomena. You see this guy that they do not match. So physics-wise, is not the model. So I want to say it's fantastically tuned, the things, okay? So I strongly advise you to have a serious reading first to Belavin polygons homology, because they put really the stage, and essentially it's my lectures up to date, let's say. What I did before with, in more detail, you will see they put down equation that you say, where they come from, these equations? So I make an effort to make you more intelligible, the paper, but read it. It's one of the most beautiful paper ever in theoretical physics, so you cannot miss this opportunity. Secondly, if you want to do really computation, and then right to the very end, because Rosenko-Patev are able to pin down all possible structure constant. It's an amazing achievement, and they do really with analytic continuation. If you learn it, you make a big step ahead in your career, believe me. Because you start handling how you do things. You analytic continue, you recover phase, you collect phases, you impose things, magically you get the structure constant. So learning the technique because it's fantastically powerful, and at the end is useful also for further studies, okay?
I think I was wondering if this, after all of this effort, is this specific for Isaac model?
No. I told you, no. This story works for any minimal models, because I'm able to quantize the charge at infinity in such a way that I get discrete value of the central charge less than 1. So holds for any minimal models, any. Okay? So the story, and it's a very, very brilliant thing, because the same field, physically, you have two different realizations, and they should coincide. It's at the same level, like the correlation function satisfies two different differential equations, but they have to coincide. So you have constraint. Doing that, you realize that the only way you can have something which you know a priori exists is to introduce screening operator. And the only way you can screen is in terms of quantized addition. So you can add 2 extra charges to compensate something. This gives the quantization on the CAS table and provide this formula. It's really amazing. Once you quantize the charges in this way, I think I wrote somewhere, anyway, so the sum of the charges has to be n times alpha plus m times alpha minus, you get exactly the CAS table. So, and then you, at this point, the theory displays full elegance, is full power, is full glory. Okay, thanks for the lecture, for being here. Been a pleasure for me, and enjoy the rest of the staying.